about the projects. So this was this week we will sort of try to define more precisely all the projects. Those people who still want to propose one, this is still possible, but I mean, you should do it this week, right? For sure. So what we also thought that it might be useful, I have notes of the discussions we had with the individual people, but it might be useful that you sort of prepare just a text with your name, the title of the project, with whom you would like to do it. I mean, with Rick, me, Augusto, okay, and then a short abstract, like a few lines that we sort of agree. And this might also a way for you to have a clear idea. I guess if you don't know precisely what you have to do, then you will find that out in writing those few sentences, and then you can come to us and ask for more details. Is that okay? Okay, so but we will, I know that there are a couple of projects which are not yet clearly defined, and so we will talk with people. I mean, Rick, Augusto, and myself, we're here this week, and so we can talk with people too.
Mark is here today.
Mark is here, but yeah, I think you talked with Mark.
Yeah, I've spoken.
Yes, and you have an idea of what you can do?
Kind of, yeah.
Kind of. So would you be able to write? Okay, so that's then I guess then that means it's well defined and it's okay.
Very well defined.
Okay, very good. So let me say before Augusto will take the floor. Let me say a few words about the solutions of yesterday. I didn't put this in. So I think the first was about pairing in a single J shell. Everybody more or less, oh, what is this exit? Yes, everybody more or less got this, I think, so this I don't need to explain. This was just to make clear that the basis used by this program is the seniority basis. Okay, so this I will not go into. The second one, most of you also got this, although this was a bit lengthy because you had to put all those correct coefficients, Clebsch-Gordon coefficients. But there is one point which was essential, which was very important, and which I would like to emphasize. Yesterday, I told you that if you have a pairing interaction, the ground state of a pairing interaction can be written like this. Okay, where this S plus, it creates a pair of particles coupled to 0. What this exercise showed that the delta interaction also conserves seniority, and no, it's okay. Yeah. It also conserves seniority, and you have now a spectrum where you have a 0 plus. This 0 plus, it has seniority 0, and it cannot mix with other states. And that means if you take a delta interaction, which is a very much more realistic interaction, the ground state has also the same structure. It is exactly the same structure, right? And this was found by several people. So if you looked at the decomposition of the ground state of the eigenstate of a delta interaction, it had also a pure character in our model, which means that the ground state has seniority 0. If you look at odd mass nuclei, so this was for J equals 13 half, right? J equals 13 half. For an odd mass nucleus, the ground state has seniority 1, okay? So the J, the angular momentum, is 13 halves, and it is pure. It is also exact seniority. It has the same structure as you would get from a pairing interaction. And so you had another 13 plus state with seniority 3, which was single, right? It did not mix with seniority 1, it does not mix with seniority 5, so it's a pure state. That doesn't mean that the delta interaction is solvable. There are many states that you cannot give an analytic expression for it, but you have a subset of states, like the ground state for an even nucleus, or the ground state of an odd mass nucleus, which are solvable and which have a well-defined structure. So that's a property of the delta interaction. So that was sort of the objective of that exercise. Okay. Let me then go to this question about seniority isomers. This was about extracting interactions from two particle nuclei. So this is nickel 70. So nickel 70. So this is 28. 42, you consider this to be a closed shell, and so this then is a two-particle spectrum, and the two-particle spectrum, this is an approximation. The two-particle spectrum defines your matrix element, and the same thing for, what was it, molybdenum 92, right, which is 4250. So this is closed in the neutrons, and then you have two protons in the G9 half. So you extract all the matrix elements from the data, okay, and then the objective was to look at the decay properties. Here they are, so it's a little table, and in particular of the 8+, because the question was, you have 8 pluses, right? In nickel 72, so that's a 4-particle nucleus, so it's 4 particles, 4 neutrons in the G9 half. Right? This state is not isomeric. On the other hand, in ruthenium 94, so this is 4 protons in the G9 half, this 8+ is isomeric. What is the reason? So you have defined the interaction from the 2-particle nuclei, and then you look at the energy of the 8+ and what are the 6 pluses, because the main decay will be by E2. And so you see there is here a 6+ which is below the 8+, but the B2 is very small. So this you could calculate by looking at the E2 transitions. Okay. But here there is another 6+ which is below the 8+ with a very large BE2. And so the transition here will be mainly to this second, the calculated second 6+, and so it will be a fast transition. On the other hand, in ruthenium 94, you see there is the 8+, one 6+ is below it, right, but with a very small BE2, and the other one is above it with a large BE2. So the decay can only go to the first 6+, so that is why this state is isomeric. This is a very simple analysis which you can do just by looking at the 2-particle spectra and then predicting something about 4-particle spectra. You can do the same analysis, for instance, for lead isotopes. We discussed a lot about lead 10, 210, so it's 82 and 128. So this is also 2 neutrons in the G9 half, but the second G9 half. So then you can predict properties, for instance, isomeric properties of lead-212 and lead-214. And you can easily convince yourself, taking the interaction here, that there should be isomers in lead-12 and lead-214. Okay. Last question. This was about SU4 symmetry. So this, first of all, this was an exercise in isospin. So you have to figure out what, so this is putting 2 nucleons in the P1 half and in the P shell, let's call it. So the P1 half and P3 half. So I did this exercise in the morning in terms of LS coupling. Here it's the same kind of problem, but now you do it in JJ coupling, so you should get the same result. And result is shown here. Let me draw it because this is a little difficult to see. So you have t equals 0 states, t equals 1 states. At t equals 1, there is a 0 plus. Then there is a 2 plus. Here the energy is -3 in units of the strength of the interaction. The energy of the 2 plus here is minus, well, I found -6/4. And then there is a final state with t equals 1. It's this one, which is at 0. 0 plus. Okay. Then we look at the t equals 0 states. What states do you have? So you have a state at -3, which is j equals 1, so that's a 1 plus. Okay. Then there is a multiplet, right, here at -6/4. These come from the diagonalization of these matrices, if necessary, right? So that is a multiplet, which is 1, 2, and 3. 1 plus, 2 plus, 3 plus, at exactly the same energy as the 2 plus t equals 1. And then there is one state, I believe, at 0, which is a 1, is a 1 plus. Okay. And so this is precisely the spectrum we obtained from LS coupling. You get the same result, JJ coupling. And you see the degeneracies, right? The 0 plus t equals 1 is exactly degenerate with the 1 plus t equals 0. So that's a consequence of the SU4 symmetry, all the degenerates here. Okay. Now this is very schematic. So this is sort of the delta interaction. It commutes with spin. It's spin independent. It's isospin independent. And so that's why you see the degeneracies here of t equals 0 and t equals 1 state. Whenever you see these degeneracies in O dot n equals z nuclei, this is a sort of a remnant of SU4 symmetry. Now, the last thing I want to say, and this probably, this was not time enough to do this, but let me sketch you what is the relation with data. If you now look, so this is just one neutron and one proton, or two nucleons in the in the p shell, right? If you look at the spectrum of lithium-6, well, what I then asked, let's now introduce a delta epsilon, right? And this is a splitting between the single particle energy of the p1 half minus the single particle energy of the p3 halves, because we know that you have some splitting, right? Then the only thing you have to do is put in delta, because in this basis this will add a diagonal contribution, a contribution to the diagonals, which can be either delta epsilon or twice delta epsilon or 0. Okay? And so then you can diagonalize the matrices, and now you look at what are the properties of the spectrum. You will find two things as a function of delta epsilon. Right? You can look at the relative energies of the 0 plus versus the 1 plus. What you will find is something like that. This is the excitation energy of the 1 plus, or the, let's call it the energy of the 1 plus minus the energy of the 0 plus. Okay? So if you introduce a spin-orbit splitting, you find that the 1 plus is always above the 0 plus. Which is a little annoying, because if you look at the data, then the data in lithium-6, for instance, it gives us a ground state, a 1 plus, and the T equals 1, 0 plus is at about 3.5 MeV. Okay, so you cannot explain with the spin-orbit splitting, you cannot explain the relative energies of those two. Then you look at the second effect, and this is the splitting of this multiplet. Right? This multiplet is seen actually in lithium 6, and so the multiplet is 3 plus, 2 plus, 1 plus. Add some energies which, well, they're given in the solution. But so the ground state is a 1 plus at 0, then the 3 plus is at 2.2 MeV, the 2 plus is at 4.3 MeV, and the 1 plus is at 5.6 MeV, and then you have T equals 0 states, and there is a 0 plus, so these are T equals 0, sorry, these are T equals 1, there is a 0 and a 2 plus at 5.3 actually. 3.6. Okay, so you see the splitting here of this multiplet, it's 3 plus 2 plus 1 plus. And if you study that as a function of this splitting, you will see that the appropriate delta is positive. That means that the energy of the P1 half, the single particle energy, should be above P3 half. Okay. So from the spectrum of lithium-6, you can actually deduce two things. First of all, the splitting, the P1 half should be above the P3 halves. And secondly, the strength of the delta interaction in the T equals 0 channel should be stronger than the strength of the delta interaction in the T equals 1 channel. Only with those two ingredients you can get a spectrum where the splitting of this multiplet is correct, 3 plus 2 plus 1 plus in that order, and the splitting between the 1 plus and the 0 plus state is correct, namely the T equals 1 is above the T equals 0. So this is a simple example of how you can sort of extract essential information or good information about the nucleon-nucleon interaction from data with a simple. Are there any questions about this? Or this is all clear?
Can you add isospin term in the new field?
If you want to include a Coulomb contribution, this can be done, yes. And this would then, you see here I have not said anything about what is the precise nucleus, right? These are all the states in lithium-6, right? If I would go to helium-6, of course I would not have the T equals 0 states, I would only have the T equals 1 state, right? So you would only see this part of the spectrum, right, in this approximation. Then if you add a Coulomb, you would add shifts. And I guess you would add, you would have some mixing, and the mixing would be between those two pluses. That's actually not so uninteresting because they are not so far apart in energy, right? So this is, in first approximation, this is a T equals 1, and this is a pure T equals 0. If you add Coulomb, then there will be some mixing between the two. And so from this mixing you could say something. Okay? So I should stop here because I'm eating from the time of Augusto. Okay. That's it. Augusto. Sorry, I've been too long. We have to use this mic. Well, we register.
Okay.
It's not too.
No, I have mine.
Oh, you have
But this is mine. Oh no, sorry, this is mine. Okay, very good. This one I need. Yeah. Hello. Oh, okay. So it is working. Okay, good. Excellent. Good. Okay, well, good morning. I'm really happy to be here. It's always good to come back to Ganil and visit with some friends, and I'd like to thank the organizers, Pete, Rick, and Marek, for the opportunity to tell you a little bit. It was okay before.
go out and in again.
Very good. Thank you. So, yeah, thank you for the invitation to tell you a little bit about pairing in nuclei. You heard a lot about pairing already these last couple of weeks. I will give you sort of a perspective from more an experimentalist rather than a theorist, although the talent program is focused on low energy nuclear theory. I hope nevertheless to convince you about the exciting things about pairing in nuclei. You probably already noticed I always like to have a little intro here of who am I. You may notice some of a connection with Niccolo. Actually, if you look, there is an extra C in the spelling of our name compared to that. I haven't figured that out yet. So whoever figures this out, I'll send you a bottle of my favorite Chianti, the Machiavelli one there, which is actually, as you see, written with only one C. So, yeah.
Maybe the second C is for cute?
I don't know. Maybe. A charming prince. So in any case, for maybe it's because of an extra Chianti, CC. So nevertheless, so yeah. The outline of the talk today, this may be very ambitious, so I may have to renormalize here as we go. We have another lecture Thursday, and so I may have to postpone some things that I plan to do today, tomorrow. We do have the hands-on activities in the afternoon, so I try to pick up there. So there'll be a short introduction and then a few things that already were discussed during the week, but I try to sort of repeat them in line with the topics that I will discuss. We'll look into the pairing and aligned coupling schemes, which are at the core of the major ingredients of nuclear structure. We'll discuss a little bit of rotational properties, which you have seen already also during the week. And then we look in detail at the pairing phase transition with the activities this afternoon, solving a 2J shell model that goes a little bit beyond to what you've done already with Pete on the single shell. So I guess you probably have had introductions this week. I think atomic nuclei offer a very unique quantum system, and it has many, many common phenomena with other subjects of contemporary research in physics, notably mesoscopic systems in condensed matter and atomic physics. And I think in particular for us in nuclear physics, these are actually exciting times because there is a convergence of new instrumentation, new accelerators, one of which is sitting right here at Gunnil, where new exotic nuclei are being produced. But once you produce the nuclei, you have to detect them and study, and new instrumentation also. Are they having a tour of the facility? No, they had. So you've seen many of these new instruments which increase the resolving power. And although they will help answering some of the questions we have now, which is more important, as is always the case, they will find new phenomena that we didn't anticipate. And I think as part of the this talent class, I think there's been this synergy now between new theory developments. People is doing now things that were never dreamed of many years ago. There is now this predictive power in theory and some kind of a synergy between experiment and theory to guide the progress in the future. You've seen this landscape. This is where we sort of play in nuclear physics. There's a great chart, and we are at the moment exploring the limits. There is the limit of isospin, where we move towards the neutron drip line, or the proton drip line. There is the limit of existence in terms of super heavy elements, and of course there is also another ingredient, which is excitation energy and angular momentum that we'll also discuss briefly during the lectures. And as you probably know from your own studies and from lectures that you heard before, there is a lot of structure physics playing roles, not only for the sake of the properties of the nuclei, but because of the paramount importance of that structure in astrophysics, for example, our process, stars, supernova, nucleosynthesis, and therefore the properties of nuclei at the streams will be of very interesting determining some of these processes. And there is many structural things that you probably discussed already, but particularly the neutron drip line, where you expect that somehow the neutron wave function, because it's weakly bound, will tunnel new phenomena related to coupling to the continuum, and of course pairing plays a major role in this region. Also in this region, and you have also, I guess, addressed some of that in Pete's and Rick's talks, there is the question of T equals 0 or neutron-proton pairing, for which the structure of these nuclei along the n equals c line are very relevant.
I left this entirely to you.
Oh, okay. So we'll discuss that too on Thursday. And of course, the question of shell stability in the island of super heavy elements, for which also pairing correlations play a major role. So pairing sort of underlies many of the structure properties, and that's the topic of these two lectures. It all started actually for nuclei in 1958, just shortly, less than a year after Bardeen, Cooper, and Schiffer proposed the BCS theory of superconductors, when giants of our field in theory, Bohr and Modelson, together with a solid-state fellow, Dave Pines, came up with an analogy exactly very similar to the concept in electron superconductivity, by noticing that when looking at the states in even nuclei excited from the ground state, they noticed that the distance in energy between that and what you would expect for a odd system was several times larger than just the breaking of a pair, and therefore they concluded that there was this correlated state of nucleons similar to that of a BCS superconductor, and that started the whole business of pairing in nuclei, which is still very timely today. Of course, many properties, not only that gap that we see there, but as we will discuss this week, you know, or even mass difference, rotational moment of inertia, and many other things that I'll show you depend on pairing correlations. And of course, as you see, and we discussed, there is common to other fermion systems, as I said, in mesoscopic system, but notably, you know, superfluidity and in particular solid state and atomic physics, quantum dots, etc. Now, 58, so it's more than 50 years already. I cannot even attempt to cover this field in 2 lectures this week, but I hope that I will be able to convey to you the excitement of this particular topic, and perhaps you get excited too, and then you will contribute to the development of these particular aspects. Now, fortunately, I have help, but I was worried that the task was so big that I worry before accepting the talk to step on those big shoes when Pete asked me. But nevertheless, I accepted the challenge, and but as I said, I have big help because there is a recent book by Ricardo Broglie and Dave Brink on nuclear superfluidity. This is a nice volume that I recommend to add to your list of books if you are interested in the aspects of pairing. I think I will attempt covering some of these aspects, but if you want to get back to some more detail, that's the book that you should have. And also a recent volume which actually commemorates these 50 years of what is called nuclear BCS. There was a 50 years of BCS volume focused on superconductors and these aspects, but Broglie and Selevinsky this time edited this is a series of articles on the application of BCS to nuclei, very, very timely and relevant for these discussions. You guys probably would like to have a copy too, or ask your advisors to have that in the department where you work. Now, of course, this is specific to nuclear pairing, but I'm sure you have already perhaps been exposed to some of these books. I just give you also for reference some others that here you should have in your library, and you may have already seen some of these. There is some of the classic books, perhaps a little bit too advanced, but those of you who will be theorists, I guess, will be exposed to this. And then there are a few articles, review articles that address the question of pairing. the original Bess Sorensen work, Broglia and company, and a more recent one by David Dean and Morten Jorgensen, who also address some of the contemporary problems of pairing in nuclei. So this is sort of the introduction. We'll go a little bit more in detail, and I will capture a little bit of things that were discussed during the week. Please, if you have any questions, feel free to stop. I hear that you do that, so I encourage that. I think it's better if you learn something than just going me through 70 slides and then you don't get anything. So the concept I will start is that with shell structure. The analogy with atomic physics is one where you say, well, how difficult is to excite a system, how high is the excitation energy, gives you an idea of how rigid that system is. And then you can go to the National Nuclear Data Center in Brookhaven, for example, and get this nice plot. And you ask yourself, what is the excitation energy of the lowest 2+ state? And you plot that as color-coded. And maybe you show that. Did you guys show the? So then you see clearly there are particular numbers where it costs you a lot of energy to excite that nucleus. That indicates that those particular nuclei are extremely robust to excitation, similar to the noble gases, and therefore there is an indication of some kind of shell structure which is present. Now we will see later that if pairing was so strong that will dominate over shell structure, this will be kind of more sort of not uninteresting landscape, but shell effects are strong enough to survive pairing interaction, and they're still there, as you can see. That doesn't mean that there is no pairing by any means. It's just that pairing is not enough to overcome. And that's at the core of the pairing phase transition we'll discuss today. Now, of course, I'm stepping in uneasy territory here, and I worry that Professor Kasten here will feel that I don't appreciate the subject of shell model. I'm not an expert, of course. I'll try to convey to you the way that I see the problem in a simple way that I'll try to capture the ingredients for what we discussed later. So, you've seen this perhaps already. The approach that I'm going to take is not the most ambitious one, which is the one carried out by a large effort in theory, which is to solve the Schrödinger equation of these A nuclei interacting by some kind of 2-bar interaction, even 3-bar interactions in an ab initio form. And I heard you have discussed that this week with Mark Caprio. There are approaches today that attempt to do that, and you can do it, in fact. It's amazing that you can. I believe you discussed rotational properties of light nuclei coming out of solving the Hamiltonian with no approximation, just the fact that you take some kind of 2-bar interaction and solve the problem. So what you've done this week and what I propose here is the classical shell model approach. We somehow rearrange this sum into a part here that sort of describes the motion of these nucleons in a mean field, which is nothing but the average of the 2-bar interaction of the other nucleons on one particular one. And then, of course, what we put here, we subtract from there, and this is what we then refer to as the residual interaction. So we have a core with a mean field, and then you treat the residual interaction in some aspects that is either effective or semi-microscopic, or the way we are going to sort of do it for the discussions today is sort of somewhat phenomenological approach. This shell model business, we take it for granted, but actually is very profound. And many of the giants in the field had thought about this. Why is it that nuclei can be described as a shell model, like, say, in an atom, where you have a clear field and the electrons moving around? And it turns out that Ben Mottelson have presented some arguments based on the so-called quantality parameter, which, if you look at a potential, and here is described for nuclear, but you can imagine of any system, there is a scale given by the attraction, in this case V0, and a size given by A. So you ask yourself, where is the quantum fluctuations, namely the kinetic energy of the zero-point motion compared to the strength of that interaction? And if that number is actually very small, as you see here, that means, for example, that you are more like a solid. The fluctuations due to the kinetic energy are not enough to overcome the V0. But in nuclei, they are comparable, in fact, and that makes this more like, as you see here, a number which is closer to 1, where these two become comparable. And this is a liquid. Now, it's a quantum liquid, and the concept of quasi-particle works, the fact that the Fermi motion and the Pauli principle allow you to talk about an orbit, and the fact that you can describe that in a mean field may be at the root. And in fact, I have posed the questions to some of my theory colleagues, actually, more in particular. I think this is a nice quantity that should be studied as we move out of n equals c into the weak binding region. What is the quantality parameter as nuclei move? Is there kind of a signal in that parameter, the kinetic energy over the potential as you become weakly bound? So this is something that to keep in mind of why is it that we are describing nuclei in this way. So you've been introduced here to the mean field. This is one characteristic of that in the form of a Wood-Saxon potential. You have orbits, of course, given the nature of the problem, and these are the shells that we see in that plot of the 2 plus energy. Now, if you were to start with a simple harmonic oscillator potential that is always being used as an approximation for a Wood-Saxon potential that will be more realistic, then you get something like that. It's a simple problem, but it's very nice to work with, and people have used this. And then you find out that at the light system it makes sense, but as you move heavy, it starts to deviate. And of course, what Pete was discussing just now about the spin-orbit splitting is the key element, who was proposed by Maria Gopper-Meyer and Jensen, for which they got the Nobel Prize. And the spin-orbit splitting is an effect that depends on the derivative of the potential and makes the high spin of the L equals, in this case, H pair split in a way that the shells that are characteristics of the harmonic oscillator on a scale like 41 to the square cube root of A MEV get modified by the spin orbit splitting. Now, because the harmonic oscillator is not really as rounded as so as flat and like this, people have added an L squared term to make it flatter and depend a little bit on L2, because otherwise the ordering of the L is not preserved. See, people have talked about the fact that because the spin-orbit splitting is the derivative of the potential with respect to R, if you go to a region where you have weakly bound nuclei, then the surface of that nucleus becomes more diffuse, and therefore you would expect some effects on the spin-orbit splitting as you move away from the stability line. Wave functions, for example, which are used in that case, showed here that, for example, the harmonic oscillator which is this potential, as we discussed, parabolic here compared to the Wood-Saxon, but the wave functions resemble one another. Of course, when you go to weakly bound nuclei, that may not be true anymore. That's one of the challenges the ab initio people have, because you have to take into account that if you have orbits that are very close to the lip, there is no lip in the harmonic oscillator and it's no tunneling. So that's serious problem when you go to very exotic nuclei to address that. And I imagine that Mark has mentioned that in his talk. Okay, so these are the ingredients. We go back to our shell model framework. This average potential, as I said, is the average of all the others in a way, and therefore you have that mean field. You parameterize that. You assume that there is a core, one of those particular nuclei which sit in the double closed shell region in that table, where both neutrons and protons are well described by an innate core. And then you have the Hamiltonian of two particles, in this particular case, say either a neutron or two neutrons or two protons, with some interaction between the two. We write this sort of schematically, but that can be cast if I take that expression that I had before and rearrange it. You can think about this yourself when you get a copy. And then you can see that indeed the Hamiltonian here, after rearranging this and relating to the fact that this is indeed what you expect very close to be the average potential, you end up having this expansion here. Core, single particle, and the interaction between those two. We can excite the core because I show you the 2 plus energy of those nuclei, so it doesn't mean that these are completely inert. So this approximation of having a core and the particles outside without affecting the core may not be so. But thanks to the fact that the excitations of those could be cast in a form which is something 2 times the, if you like, the excitation energy of the harmonic oscillator. This term is large compared to the residual interaction, which is about 50 MeV over A. That's, you can, maybe we'll do that as an exercise this afternoon. Think about it, and then you show me why that is. But so essentially, this can be perturbably treated, and therefore it's not so bad that you can take the core as an inert core. Then, of course, there are refinements of that, and people have done that. In particular for pairing, as I'll show you on Thursday, this core polarization is actually extremely important. But for the moment, we assume the core is there. And note here that if I were to make this ratio, it turns out that the effective interaction divided by the separation scale as a to the 2/3. So this effect may become smaller and smaller. So I think that tells me that, for example, calcium-40, we should discuss this if you guys agree, but the calcium-40, which is 2020, a closed shell nucleus, is actually less magic than lead-208. So my argument is that the residual interaction actually diminishes with the size faster than the shell. That goes like a to the 1/3. And although there is a degeneracy, it's, so lead-208 is a more close magic nuclear than calcium-40. In fact, calcium-40 is not a very good class, but nevertheless, think about it. We can discuss that in the afternoon.
There is a little nesting on transparency 80 -
Oh, well, it says decreases. So, but yeah. Okay, so now residual interaction. That's the aspect that we are going to address from now on. And you have chat about that at length probably this week. I'll give you a little take of my own on this subject. So as I said, you can derive that from basic principles, the nucleon-nucleon interaction. You do all the things that you have to do there to take into account median effects, and people are doing that. As I said, the ab initio methods allows you to do that, effective field theories, approaches, etc. You can actually determine the residual interaction from experimental data by using that expression that I assume I have a core. So then I can go to different cores and determine for the 2 nucleon system, so take calcium 40 plus 2 nucleons, or lead 208 plus 2 nucleons, and I can locally determine empirically the effective interaction of those 2 nucleons, and then learn about the properties of those 2. Pete, I think, already alluded to that with the example of the lithium-6 and helium-6. In fact, I'm going to propose to you to estimate the strength of the pairing from helium-6 and see what we can say about pairing in heavy nuclei if we were to extrapolate from helium-6. And then once we have these, you can input that into a big shell model code that takes into account those basic matrix elements, and then do all the algebra related to that Pete, I'm sure, already discussed. And I guess you have already some tools in the R model program that allows you to do that and do more complicated systems. There is another approach, which is also, once you know about the residual interaction, you can then use a schematic model which captures the main ingredient of that interaction in one form or another, and for which there are tools to solve the many-body problem either exactly or numerically in a simple way that allows you to treat more complicated nuclei. So we will look at these 2 now in the rest of the lecture. So 2 references that come to mind, which I always like in this aspect, is a famous paper by Schiffer and True, and actually one that is not as well known, but the fact that Hans Bethe was there makes it important to me, and which is how to derive that effective interaction from experiment. And essentially the approach is that the one that Peter was alluding this morning. You can do that in a more complicated way when you go heavy, but essentially you look at a core with closed shells, again lead 208 for example, then you go to bismuth 209 on lead 209, those are the 1 nucleons. You determine the binding of that proton or neutron in that core, and then you look at the O-dot system, in this case that has the NN or PP or NP, and then you take that and then you calculate the binding difference, which tells you how much of a residual interaction you have for that J1 and J2. Because you have the different couplings, so you can couple, say, 2 particles, one in J1 and J2 to a multiplet of spins, you can actually calculate a Schiffer parabola and use a normalized way to present that, as I will show you next. So here, and it's very intuitively actually to present the results in the form of an angle. You imagine yourself, you have these spins, and these orbits tend to be perpendicular to that angular momentum, and it's indicated by that. And then you can calculate the angle in a sort of semi-classical way by looking at the coupled spin. So you couple those 2 to J, and then using that and the information on J1 and J2, calculate an angle, and then look at the dependence of this interaction as a function of the angle. So because we know the nucleon interaction is short range, you would expect that this will be maximized when? If I have these angles, when will be the maximum overlap? Indeed, that's the concept, and this angle gives you that overlap visually immediately, and therefore when you plot, for example, now t equals 1, the T equal 1 states that Pete showed earlier, for example. Now I go to many nuclei here. You see P3 half, that's Pete's case, and then D3 half, etc. And then what you see, indeed, that when you have a 180-degree coupling, namely one particle going one way, the other one, but maximum overlap imposed by the Pauli principle for equal nucleons, then the energy is quite binding. So already there tells you that the nuclei like to pair. But this, the nucleon-nucleon interaction already favors the formation of pairs. Now, as you open the angle, the interaction becomes less bound, and then there is this sort of trend that favors the 180 coupling. What happens on the T equals 0 channel? Now you can couple both the neutron-proton to T equals 0, T equals 1, example we just discussed. Now for that one, you can still couple the neutron-proton pair, of course, at 180 degrees. That also gives you maximum overlap. But also you can now couple, because they are not bound by the Pauli principle, you can also couple them to high spin, which are extremely important for the isomers you guys just discussed before. You can have, say, a d phi half neutron and a d phi half proton and couple them to 10. They overlap very largely, and therefore it actually bounds even more. So the T equals 0 in the high spin state is even stronger than that of the pairs. So that's the property of the interaction in the T equals 0, J equals odd. So if you look at either Schiffer or the other paper by Molinari, then you can convince yourself that a major ingredient of this interaction that explains this is a delta function, so-called short-range interaction, like you discussed this week and week before, that likes this strong overlap with some constant G that will be the strength of that part of the interaction. But that's not all. In fact, you cannot describe all the data without a longer range force, and that usually parameterized by a Legendre polynomial of order L, and the strongest term that comes out is the quadruple term. And that is so-called the quadruple correlations. And actually, the range of this in angle is, this is infinite small, this one is larger, and that gives you the seed for quadruple deformation that you have seen already during the lectures this week. And the parameters that Molinari quotes are about 20 MeV over A and 50 MeV over A for those parameters. And we will look into that a little bit more as we move forward. Actually, I have G and V2 like a energy scale divided by A. Why? Why should it go like 1 over A? Why shouldn't it go like A? So if you were to repeat the analysis of Molinari and Schiffer and True, and you look at the strength of these matrix elements or strength of this interaction that I put here, you find that they scale like 1 over A. I mean, not completely 1 over A, but they decrease with A. Now I'll show you here a plot from another nice report of Denick, where he shows this average energy that I showed at the beginning, which essentially gives you the size of that matrix element. And you see that for the P3 half here in lithium is very large, But then when you go here to 200, it goes down. And the question is why? You answered earlier about the reason why it's strong. What was that? The short range, yeah?
Yeah, but I don't, because the volume goes as A.
Yeah.
But
So
the distance between the particle doesn't go as A. It stays more or less the same.
no, if you have a volume which is bigger,
No, the average distance between the nucleus is more or less the same. They're like some cards here somehow. The distance between neighboring nucleus.
no, they will go like if you have a bigger size,
the
the time.
nearest neighbor is always more or less sitting at the same distance, above something.
Well, I'll propose to you that you calculate a matrix element when you have, say, a delta interaction, and you assume that they have to interact when they are on top of each other, and then you calculate the wave function of that nucleus in a simple approximation, then the probability of finding is 1 in the total volume. Therefore, the probability of finding one and another one close by goes like 1 over the volume. You have a bigger volume, the chances that these two nuclei interact.
But we have also more nuclei.
The what?
We have also more nuclei.
Yeah, and then we will see that goes because then the energy, which is then the Hamiltonian, of course, takes into account that you have more, and that's exactly what we are going to discuss now. So, for example, if you have a quadruple interaction, you are going to have the probability of interacting more because you have more neighbors. If you have a delta interaction, you saw that it only interacts with the near neighbors because it depends on the number of pairs. And actually, you can actually calculate the volume is R squared and say, and that actually, you see, this is 1 over A, the red line here, which is a little bit stronger than, in fact, if you take the harmonic oscillator wave functions, you may get like it's more like A to the 1/3. He determines 3/4. So the average strength scales like 1 over the size. So if you have a lead to oil again, as we argue, and that actually goes back to the so the average mean field is the sum, as we wrote it schematically in the beginning, is the sum of this average Bij, and so you have A average Bij because you have A nucleons, and you know the depth of the potential is constant. It's about 50 MeV. So this means that the average interaction should go down like 1 over A. Okay. So when do we? Oh, 10:30. Okay, very good. So let's go now and take advantage of what we just learned about the nature of that residual interaction and try to see what kind of coupling scheme will be favorable for us to take advantage of that. How do the nucleons will couple in order to maximize that overlap? And so I think you have probably discussed this with Pete already. And essentially, as we argued before, based on the parabolas or the curves of Schiffer and True, we see that the maximum overlap occurs with 180-degree coupling to n equals 0. And if you were to write down a wave function that will look like that, you will have some kind of harmonic oscillator, Legendre polynomial wave function angular, which will depend on the L0 coefficient here, and then this sort of looks like that. So they like to concentrate in a region here that depends on the L. The larger the L, the more concentrated they are, and they take advantage of correlations on radius, which are of the order of the radius of the nucleus divided by L. So you can see immediately that as you open up, then the distance here becomes I r over L. So then any state that is not the 0 plus essentially becomes unfavored, because the distance on average now increases beyond this region where the delta acts very strong. And therefore, when you have an attraction like that, and then you saw, I'm sure, with Pete about the seniority discussions and the delta that we just heard this morning in the example, you imagine, and you can look at lead-210, for example, two nucleons, 2 neutrons above 126, the closed shell, and then you see this sort of pattern where the 0 plus is depressed compared to the rest. And when you look at the spectrum, and now you know how to calculate that with the delta, you'll see something which resembles that. And I don't know how to do that, so we'll do sort of a simple pairing interaction. We just assume a constant matrix element that I still call G and the delta. So essentially what you do is you just project, and only the 0 plus goes down, and then you make all of them degenerate, and then this one, and in that way it's very simple to solve the problem, because your ingredients here in a single J, as you know that, probably you know it better than I do now. You have n particles in a J with a degeneracy omega. You like to make those pairs, and then your wave function is essentially a creation of those pairs in the ground state. And then under those circumstances, you can write that the pairing energy is this constant G, which is the strength, about 20 MeV over A, as we showed before, times the number of particles minus the number of particles which are not paired. This is the seniority that you were just discussing with Pete, and times the degeneracy of the system. The larger omega, so if you have a P3 halves or you have a I13 half, the pairing correlations will like the I13 half better because omega is larger. So you can gain energy by having more particles, more degeneracy. So you can rewrite this in many different ways. But essentially, you can approximate this simple expression if you are in a large shell, much larger than when you can essentially, for seniority 0, you can write this as n over 2. So I rearrange that and G omega, which you can now again rewrite as the number of pairs, n over 2 times twice a gap. So this is the energy that costs you to break a pair, and that's so-called the pairing gap. And essentially, you see the argument we were having just before. This goes like the number of pairs, and the reason is because they actually need to be very close to each other. So it's only those pairs that are correlated that contribute to the pairing energy. And you saw that early before for the case of the P3 half. And I saw an example that you did yesterday for the I13 half, if I'm not mistaken, to calculate the energy of the ground state. Now, an interesting thing was pointed out that by Chris Heide and others in this reference here, which is the fact that although the spectrum I show you here before looks very similar. When you look at the actual binding energy of the system, it's not. Actually, if you look at the delta interaction across a shell, the delta interaction continues rising while the pairing has a parabolic shape that bends over, because when you close here and there is sort of similar, giving the symmetry around mid-shell. And the reason why is that is because although the delta is a very short range interaction, it has all the other multiples on it. And as we will see next, the other multiples take advantage of the longer range, and now the energy can increase more than that with the number of pairs that we'll see next. So this is a picture you're seeing based on this simple seniority with a constant pairing matrix element. There is a characteristic even gap. That's the gap that Bohr, Mottelson, and Pines observed and led them to propose the BCS approach to nuclei. You see the state here, the ground state, spin 0, is strongly bound compared to the rest that lies somewhere there. And in this simple picture, if you now add a particle to it, as Pete was arguing, it lies right there at the same energy, if you like. And while a sort of a linear extrapolation will put it in here, if it was just a linear relation as shown by the n over 2. So the next even lies there, and this distance again is twice the gap. You have an odd system, it's also there, so this is twice the gap. So this already suggests a way for us experimentalists to determine the size of this pairing gap. I can take an odd system and compare to the average of those two evens, or I can go to an odd system and compare to the average even, and look at that distance and determine a quantity which resembles that gain in pairing energy due to the delta or pairing interaction. And of course you can do that. And for example, if you look at TINS, let me go, yeah, you can do that if you go to Bohr Mottelson, for example, or any other of the textbooks in nuclear. Then this is derived, say, for protons here, and you can see this nice expression here that sort of correlates the data, and you can see the gap in this. They parameterize this as something of the order of 12 MeV over square root of A. So indeed the gap, as we argued before, because the gap is strongly depending on the strength of the force, that strength we argue was about 20 MeV over A. The gap is not completely 1 over A because it's not exactly the strength of the force. It goes down slower than that 1 over A is a square root of A, and therefore you see this decrease in the data. So again, as we argued before, I mean, this average interaction at the beginning, we say decreases with A, and you see that also here. The pairing correlations here are less strong than they seem to be here. And the pairing gap, if you go back to the expression we had before, remember that it includes not only the strength, but the degeneracy. And the degeneracy increases the larger the system you have. For example, in lead 2A, you will see an I13.5 level, which you don't see in lithium. And therefore, the gap will increase with omega, but omega increases less faster than G, and that's why you see the gap going down still with the size of the system. And coming back to this plot, the argument was you will see something which resembles a 0 plus and some excited state at an energy of 2 delta. And you can see, for example, the example that I wanted to show you is the tin isotopes, which are the classic example of the seniority scheme or a BCS condensate. And you see the 2 plus energy is very, very smooth. And all across the change from 100 to 132, it's about 1.3, 1.4 MeV. If I would estimate twice the gap, it will be here. So it's actually a little bit less. And the question is why that is. And that's because, of course, as we'll argue next, it's not only pairing, but there is something else, which is the quadrupole correlations, as we discussed before. Yes? The what? Probably 11, sorry. My bad. 1169. So, but you see that rather constant, and this is indicative indeed of the presence of pairing, because pairing washes out, as we argued before, if you mixes all the levels and then it sort of makes everything look the same. Not at tin 100 and tin 132, because they are not enough to break the shell if you have only one. Please.
I was just going to say, why aren't we plotting the energy divided by A? Or is that what's happening? It's just...
You mean in this here, in this plot?
No, in the pairing plot. Or I guess it's just G that depends on A.
So if you have in this simple model, as you can see, I have defined the gap as G omega. And the reason, because you have pairs, and we will see this afternoon in the activity where you actually will solve this problem numerically. Essentially, the pairing correlations thrive by scattering pairs from one level to other. And the more degeneracy you have, you can scatter. If you have only one level and next one half, you cannot scatter anything. It's just there. It could be, it's like the high spin. You can have an isomer. The isomer is very, very bound, but it's not, it's very unique state. It's just one pair. Here you have a very mixed wave function that is the mixture of all pairs. We'll see that this afternoon when we look at the wave function in detail. Now in this plot, I just put a constant pair. There should be actually a little dependence here because the gap depends on the square root of A, and so it will be the square root of say 100 compared to 132, and the gap will go down a little bit. But in this small scale, it's probably not major. And so yeah, I'll show you that gap when you look at the overall picture. Now you see locally you have large fluctuations for that, because at the end pairing is not so strong that it washes everything out. You still have left some shell effects there, or quasi-particle effects, that still give some identity to each nucleus. If, as I said, if pairing was so strong, they would be very boring. Now, of course, this parametrization of Bohr-Mottelson is being around for many years, and a quick estimate, of course, 812 over square root of A will put you close to where we should be. But there are other prescriptions here, at least one that I like in particular in this paper. And I like it because actually, if you were to use harmonic oscillator wave functions, then G we say goes like 1 over A, and then actually in the harmonic oscillator, omega goes like A to the 2/3. So then the gap should go like 1 over cube root of A. And I like that parametrization myself because they do pick that one. And of course, because we know that the mean fields depend on the NZ or isospin, if you like, then there is a dependence on n minus c here that is taken into account in these more detailed expressions that go beyond the simple estimate of Bohr-Mottelson, if you want to have that at hand. You see here, this seems to be a little larger for protons. We will go back to that on Thursday, but I'll keep that in mind. Try to think why would it be that this main strength here is larger for protons than it is for neutrons. Okay, now let me see. Few minutes. So yeah, single shell, 2 single J shells like we do this afternoon are very good toy models. We can learn a lot about the basic physics, but in terms of going a little bit further and having a realistic nucleus, it becomes a little bit more complicated because a nucleus is not a 2J. Maybe the lithium-6 you can get by, but if you go to teens, for example, the one that I showed you earlier, it will not be easy to convey that you will have only 2 levels or 1 level. Here, then, is how to make it a little bit more realistic, and of course, I cannot but refer to that first paper by Bohr-Mottelson and Pines, who took essentially the ideas of the BCS equation and translate that to nuclei. So you have a Hamiltonian that has the single particle energies. There is this 2-bar interaction, which for simplicity we again are going to make independent of the orbit. So that's an approximation already in itself, but for me I don't think I can go much beyond that. So we just take a constant matrix element, and the question is how to solve this Hamiltonian. Now, of course, if you are ambitious, of course, you can do an ab initio thing, and it will be there. It has to be there. But some of these wave functions, like particular this one here, will take some time for an ab initio calculation to get out, because it's a very complex beast. And what Bardeen, Cooper, and Schiffer, after the work of Cooper, finding out the importance of this correlated pair state of electrons, came up with a wave function that takes into account these correlated pairs in some kind, this form, which is essentially, if you like, the one that we just wrote for the ground state in a single J, is some kind of product of these pair operators on the vacuum. And so if you write that, and this I'm still amazed that these guys figured this out, but they did. And so you can actually write now with this wave function, you can work the Hamiltonian, and then you say, well, I'm going to solve this Hamiltonian with some requirements. And one of the requirements is that because this wave function does not conserve the number of particles, that you actually impose that the number of particles on average is the number of particles of your system. That's not too bad in solid state, where you have, I don't know, 10,000 electrons in your wave function. Here is maybe 100 nucleons at the most. That could be a problem. And there are methods to go beyond that, of course, number projected, BCS, etc., that I cannot cover in these lectures, and I will not even dare to do so. but essentially there is a gap equation. You can solve this, and we will do that in the hands-on activities probably Thursday. Essentially you start with the gap equation, you determine these U and B factors as a function of these two ingredients. The one is the pairing gap, which is related to the G as you see there. And also the fixed parameter here, the average is this Lagrange multiplier, which is the Fermi energy. So you do that, you iterate a few times until the system converges, and the output of that is lambda and delta, and we'll see that in the hands-ons, as I said. There is another way of looking at this, a so-called a mean field approach. So essentially, you assume that you have a mean field, and then you write the equation in this form, where the pairing gap is that average of the pair operator, and you actually introduce now the concept of quasi-particles. So the original single particle states are transformed in some kind of linear combination of particle and holes. And now the energy of the system is not longer this one that you see in the single particle, but the energy of the quasi-particle is measured with respect to the Fermi surface, and there is always an energy of delta that caused you to generate that pair, and the curve, it looks like this. Now, this looks like this, and the occupation, so this UV looks like this. So if there was no pairing correlation, everything which below the Fermi surface will be populated with probability 1, but because now pairing takes into account, then it smears the Fermi surface by an energy of order delta, and now the orbits that are near this region, you can see will be partially particle, partially hole, so it's a mixture of both. As you move away from the Fermi surface, either down or up, then the energy you see becomes essentially that of a single particle. So the action happens in a region which is about delta plus or minus delta near the Fermi surface. The rest is so this is the pairing phenomena is an important effect that happens near the Fermi surface. I guess this is about time, isn't it, for coffee?